transmitter. So let me record. Okay, so we'll start the session. So as we'll have a look on the project that we need to work around, right? So you can see here, this is a specification of a simplified UART protocol. So we know UART, right? What is UART? It's an asynchronous serial communication protocol with configurable different speed. Speed is here the baud rate. So here you can see one UART and another UART is there. So I'm transmitting data in serially. The UART RX will transmit the data, TX will receive it. Similarly, you can see here from RX to TX also the data will be transmitted. So in this mode, we can have full duplex communication. So this thing we need to implement, right? So we can see this is the data frame. So for our project that we are working on is one start bit with 8 data frame and stop bits. If you want, you can include priority bits also, correct? So mainly there will be 3 blocks that you need to create. So this is full UART, baud rate generator, receiver, and transmitter. And this is how we'll be creating different baud rates. So you can see here, to calculate different baud rates, the system clock of UART is 1.8, but my FPGA clock is 100 megahertz, right? If you select that board. So we need to divide it first to 1.8, and from there you can see multiple different baud rates that they have created using this 8-bit counter. Just go through the spec. Let me know if you have any doubts. You can see here it's simple calculations. So depending upon different state of the multiplexer, we can have different baud rate. And while we are transmitting the data, it will be in one baud rate. And when we are receiving, it should be a bit on a faster baud rate. You can see here. So why? Because we have to maintain the Nyquist rate, correct? So here we have taken 8 times faster to sample the data, right? The data will be transmitted in baud rate only, but to sample the data, we are sampling it 8 times faster. You can see here. And this is the internal architecture, and this is the, you can say, the algorithm. So from this algorithm, you have to write an FSM. So that will fit inside this. And these are basically bit counters, shift registers, and these are rising edge detectors. I guess all those things are covered. So just as per this, as per the requirement, you just need to connect all those things and need to implement, right? So this is for the transmitter. What it will do, we'll be sending 8-bit data, 1 by 1 bit data it will transmit, right? So you can see here. So that transmitted data should be serialized. These should be deserialized, and it should be put into 8 bits data frame. So that is the architecture here, right? So the step-by-step process is also given. So what you need to do, you have to code it. First, you need to code it. You have to verify it using a test bench. Then after completing that, you need to, we can give you board access, we can implement it. So here you can see this is some simulation results. This is how we have to send. So A5 I am sending. So this is how the data is transmitting, and it has received. You can see here I'm receiving A5, correct? And you can see this is the FPGA implementation. So this switches, I'm sending the data to those LEDs, and this switches, it is sending the data to those LEDs. You can see. So this is how I'm doing full duplex transmission, right? You can see here. So from one point to another point, I'm sending data from between 2 FPGA boards. That is the requirement. So this is the specification. Depending upon the specification, in detailed specification we have been given. That is the architecture. This is the FSMs. Using that, we need to create this design. Is it fine?
Yes, sir. Sir,
Okay.
for receiving, you said you took 8 times of the baud rate.
Yes, correct.
It can be more than twice. I mean, it can be thrice like that.
Yeah,
Also.
more than twice. Yeah. Yes, correct. But what happens? We need to like if I'm taking 8 times, that is well and good, because I'm trying, because the date like I'm trying to sample at the at this point, at the middle point of the data the serial bit is coming, right? I'm trying to sample at the middle. So if you have more powers of 2, let's say 8 times, 16 times, or I can say 32 times, we'll have more finer control on that. So 2-3 times we might miss the sample at the center. We might sample at its edge. So it might not properly sample the data. So that's why I'm going for higher clock frequencies. and already I have higher clock frequencies, so it is like good for me to generate it, right? So that is not, we don't need to, so directly you can see here. So here I'm dividing, and without dividing only, I'm taking the clock, that is 8 bits. So directly I have higher 8 times higher block, this one, clock frequency, like baud rate frequency. So that's why directly I'm taking it out. Is it fine?
Divide by C, what does it mean?
Okay, sir.
Divide by, so you can see here, you can read this. So 8 samples are there. So 8-bit data frame, right? So that's why we're sending right there. So divided by C means C is 8 as per specification, you can see. Because we are sending 8-bit data. Okay. Just go through this spec. Start trying to work on this. So what you need to do, you need to have four Verilog codes. So one will be the baud rate generator, one will be UART receiver, another will be UART transmitter. First, you write a Verilog code for baud rate generator, and you try to come up in simulation this many clock frequencies. That means this many baud rates, right? If it is done, then what you can do, you can write the code for UART transmitter. Then you can connect baud rate and UART transmitter, basic instantiation, right? Then what we can do, we can send data. Let's say I'm sending A5 data. You can see here A5 data, and I'm receiving it. So like that, you can send those datas, and you can check the TXD signal. If it is also working, then what I'll do, I'll go to the next step, that is UART receiver. So what will be writing the code for UART receiver to receive those serial bits, and finally I should get A5 on this output. So once all these three modules has been coded, I will have a top module, that is UART underscore top, through which the input and output will be connected with XDC file, and I'll be simulating it. And if required, inside, like with the system also I can connect. We can have ILAs or VIOs, and we can integrate it to the system. So that is step by step. You can break the design. If you can make it into groups, and also you can work it out. Fine, right? Okay.
Yes, sir.
Fine. So yesterday, one of the participants asked to have a that difference between VIO and ILAs. So that difference will take, and then we'll be starting a new topic, that is Zinc SoC. Fine. So we got to know about Vivado Logic Analyzer, right? As of now, what we have discussed, we got to know about Vivado Logic Analyzer. Basically, we are doing this. You can see here. Just yesterday also, what we have done, this is user function. User function in my case was a counter. Using this user function, using ILA in both the ways, we have transmitted the data to the debug core hub, and we have seen the waveform that is captured from inside the chip to the design, right? So here we have the debug cores. We have two types of debug cores. One is ILA and another is VIO, correct? So both has different, like you can say, advantages and disadvantages, you can say, right? So that thing will lead here in debug course, right? So we'll have an introduction about, we'll have the specifications about ILA and VIO. So first we can see this is ILA. This is the ILA code. So we know we have trigger ports, and we have probe ports, and there is a clock. And trigger in, trigger out acknowledgements are there, so that we can trigger the situation. Trigger means we can capture the data at a particular standpoint. So how many probes I can have maximum? You can see I can have 1024 probes, and each probe can have 4096 signals. That is the amount of connections I can do in one ILA core, in one clock domain, right? And what is the advantage is, these probes are unidirectional. Unidirectional means this is my design. So internal of the data also I can take. So from the input and output after the buffers also I can take, and there is no direction. Directly it will go inside the ILA, because all the things will be captured. It can be an input, it can be an output, it can be an internal register. Okay. So this is one thing in ILA. So in case of VIO, you can see here, in case of VIO, these are limited. So main thing is that, let's have the main difference that I need to say is, here we'll discuss this. So the main difference between VIO and ILA is, VIO works on the input and output interface only. So let's say this is my design. Let's say I'm taking this UART design. That is where you're working. So if I want to connect VIO, let's say I want to connect VIO at the output, right? I want to connect 8 virtual LEDs. 8 virtual LEDs. So how to connect that? How to work it around, right? The main thing is that I will connect this UART top module. So this VIO will connect at the interface level only. It will not connect at internal to the registers. VIOs only connect at the interface level. Interface level means you can provide inputs, you can provide outputs. So you can, so this VIO core can, one VIO core only, it can provide input and it can accept output. But ILAs, what it can do, let's say this is VIO. VIOs works in input and output. ILAs, it can go inside the registers, it can go at the inputs, it can go at the outputs, and it can probe the data. This is the first difference. So second difference that I need to see is all the input probes in all the probes inside the ILA are all input direction. It goes in one way only because it can be an input, it can be internal registers, it can be output, input or output. All the things will be captured depending upon the trigger situation. But in case of VIO, you can see. So let's say this is my design. It will have inputs and output. This is my user design. It will have inputs and outputs. So I want to connect a VIO. So VIO, what it will have? It will have virtual inputs and virtual outputs. So how to connect that? In case of ILA, we don't need to see what is my direction of the data because all will go as an input to the ILA. But in case of a VIO, the output of VIO should be connected to the input of the user design. Because it works at the interface level, right? So if I'm, let's say I have some switches in VIO. So that switch should be output. And that output should be connected to the input of the user design. Or you can say user logic. Then only the VIO can control the user design, right? And the output of my RTL code should be connected to the input of the VIO. This is output of the user design is connected to the input of the VIO. And the output of the VIO is connected to the input of the user design. So let's say my user design is a counter, 32-bit counter. So the output of the counter, that is the register, will be connected to the input of the VIO. So here those LED, 32 LEDs will be there, right? So here LEDs will be there. And here the switches will be there, basically. To control the up and down, the reset, all those things, the switches will be there. Correct? So that will be going from the output and it will go to the input of the user design. So this is the connection that you need to follow when you are using VIO. This is the second difference. The third difference is, in case of ILA, we have seen, right, we'll be triggering it and using this trigger, using this trigger, I can get the past input and the the future input after the trigger. You can get like after the trigger, what were the condition of the chip, or you can say what is the condition of the data and of those registers, and after the trigger also what is the condition. So all those things I can get in a timescale format. But in case of VIO, I will get only the present data. It is like a LED switch or any kind of an input-output device, right? Only the present data I will get. I will not get the previous data. There is no triggering mechanism in VIO. There is only connections, like it is connected to some virtual LEDs, virtual inputs, and there is no kind of a trigger condition to see what was the previous input, what was the situation after the trigger, what is the previous situation before it. There is no concept of trigger. We cannot control it. Once the system is started, the virtual input output will be executed. But ILA, what we can do, we can create some trigger conditions here. You can see, depending upon the trigger condition, we can capture the data. So these are the main difference that we need to follow. So now, in your case, let's say I'm implementing a FIR filter. I'm giving an example, or certain. I'm giving a more basic example. I'm applying a shift register. I want to see a shift register code. So I want to see each and every bit shifting at each and every stage by stage. So that's why I will be using ILA. Let's say I am working on a simple AND gate, OR gate. I just want to see the LED blinks. Depending upon my requirement, then I will use VIO. So whenever there is requirement that there is a sequence of data I need to check, there is a sequence of conditions that I need to check, I will be preferring ILA. Is it fine, participants?
Yes,
Abhinav?
sir. Yes, sir.
Okay, fine. So I have provided you with some reference.
Yes, sir.
So please go through those reference. Let me know if any queries you have. Fine. So here we'll stop with the FPGA sessions, and we'll start with the Zinc SoC sessions. Right. So before that, we should know about the concept of embedded system. So we'll have an idea on it. So what we have done basically in the Vivado tool, we have developing hardware. So now, as we know, we have Zinc SoCs. So this is a technology that has been invented by Xilinx. They were the first to come up with this all programmable SoC, where they have the FPGA fabric. Along with that, they have a processor chip inside the chip itself, like a processor logic inside the chip itself. That is ARM core. So ARM plus FPGA, they call that an all programmable SoC. All programmable means we can program hardware, we can do hardware programming on FPGA, and we can do software programming on the ARM. And they termed it as, they trademarked it as Zinc 7000 SoC. So this is what will be working around. But let's say I don't have ARM. I have only FPGAs. But I need to
Sir, ARM stands
have
for?
advanced RISC machine. It's a microprocessor core.
Oh.
Correct? So
Actually,
it's
I
a
don't know
basically.
it.
Oh, okay, fine. No worries. So I will give the what is ARM? What is the what ARM? How it came? So basically, ARM is a different company. First of all, so ARM, what they do, they don't manufacture chips. You cannot see any chips that has been manufactured by the company ARM. What they do, they make ARM core. So they have A series, they have R series, they have M series. So those ARM core, they provide it to other companies like Qualcomm. So we have all in our phones, most of our phones, we have Qualcomm chips, right? So Qualcomm uses ARM core and they customize it depending upon their requirement, and they come up with Snapdragon. So if you see inside Snapdragon, there's an ARM core. So there's a huge ecosystem built around ARM. So if you go for any kind of a vehicle also, you'll be using ARM core. If you go for any kind of a process instrumentation kind of a facility, you will also see those ARM cores. So basically, this ARM core is a processor core. And like STM Microelectronics, they use this ARM core and they make their own microcontrollers. Xilinx, they use this ARM cores and make their own SoC. So this ARM core is very versatile. And there's a huge ecosystem around it. So from a embedded system application to simple embedded applications to a quite complex, right, ladder or military level system application, defense level system application, everywhere ARM core is used in some bits and parts. In case of Qualcomm processors, also you can see, if you see any kind of a RISC processor, basically the idea is on ARM itself. So ARM is a processor core. So that means it's a microprocessor in simple terms, if you see, right? So that microprocessor is already been implemented inside the chip. So this is a hard IP. And so what is the advantage? I can have ASIC like controlling of ARM inside the chip also, and that can interact with my FPGA, and I can build a system which has ARM processor as a hard IP and also some programmable devices like FPGAs. So that is the idea about Zinc 7000 SoC. Is it fine, sir, as of now?
Yes, sir.
So let's say,
Sir,
yeah.
Sir, ARM is SoC or ARM plus FPGA is SoC?
So this ARM plus FPGA is all programmable SoC. Correct. So SoC is actually this is Zinc SoC we are focusing on. So SoC is a very huge topic. If you see, just let's say I'm giving an example. Yeah, if you see a Qualcomm chip, let's say like which is in our mobile phones, they will have some ARM cores. They will have some GPUs nowadays. They will have some DSP cores. Nowadays they have antennas also in one chip. So system on chip, if it's very generic term. So whole system it is inside in a chip, right? So this system on chip is a conceptual term, you can say. Yeah, but what we are focusing on Zinc 7000 all programmable SoC. So in this case, we have ARM plus FPGA fabric only.
That I mean to say that ARM plus FPGA both you can say as SoC.
Both you can say
because
it is
here
an
the
SoC.
example.
Yeah.
Okay.
Yeah.
Okay, sir.
Correct. It's in all. So that ARM plus FPGA concept was invented by Xilinx. So they have their own 7 series FPGA. Along with that, they have included ARM. Then they have fabricated the chip like that, and they termed it as all programmable SoC. But the concept, the overlining concept is an SoC. So so this is a type of an SoC, you can say. But there are different types of companies. They create their own SoCs.
So I mean to say that on the PCB, you are having a Zinc processor, okay, and you are showing us there is an FPGA. So whether ARM is inbuilt inside that particular IC or it is a different IC on the
That is what I'm.
PCB.
No. Yes. So we have seen the Z board, right? So in Z board only, there is a full one chip is there. Inside the chip only, this ARM plus
Yes,
FPGA.
got it, sir. Got it. That is SoC.
Yeah. So this is system on a chip. So you can see we have this. This is called PS. This is the processing system, and this is the programmable logic. So both the things we are inside a chip. So full system is inside a chip. So that means using ARM and FPGA, I can make a full system that will be inside the chip. Previously, that is what I am telling about. Previously, what was happening? Because this technology came in 2013-14 at that time, SoC concept, right? Before that, we have only FPGAs. Some faculties might know they have previously they have worked on. So separately there was a microprocessor core. It can be ARM. It can be like Power PC kind of a thing. So that would be controlling the FPGA. So it was only an FPGA fabric, and there is a microprocessor separate out of the chip, but on the PCB. But what was the issue? There are lots of many latencies. The PCB lines, it was very difficult to control, and plus there are multiple protocol transactions, multiple interfacing we need to do. So that's why we Xilinx came up with a better solution to combine these two things inside one chip, and it became a system on a chip. And we'll see now what is the concept of SoC. That is Zinc SoC. What are the interfaces available? All those things in the subsequent discussions. Right? Now, as I told, we got an idea about Zinc SoC. Mainly the objective from now, it is to create an embedded system. So what happens in an embedded system? What is an embedded system basically? It does a specific work. So full system will be designing inside a chip itself. So what we'll do, we'll write a C code using certain tool to the ARM processor, or I can say in microprocessors or microcontrollers. If any some labs we do, what we use a software defined kit. We use Eclipse, we use Keil, 8051 we use Keil, right? So that what it does, it creates the hex code that will go to the DDR memory or the program memory of the processor. So that will be done by the VITIS software development. So now we'll have to migrate into multiple tools. And the hardware design that I'll be including the ARM processor, I'll be including configuring the ARM processor, I'll be creating certain RTL codes, that is digital hardware. All those things will be done by the Vivado hardware development. That Vivado tool only that we are now familiar with will be used to develop the hardware. VITIS will be used to develop the software. Now the work will be divided. Then we have other tools that is not in this part of the internship. We have VITIS HLS to create IPs using C and C++ code. Then we have MATLAB system generator. So what we can do directly, MATLAB scripts can be converted into hardware IPs. So MATLAB algorithms directly converted into hardware IPs. So all those IPs, we can include it in Vivado inside the IP catalog, and I can build a whole the hardware of the embedded system in the Vivado design suite itself. Then I can provide to this VITIS IDE software development that particular hardware files. You can say hardware files. Those will have its technological name. I'll let you know. And on that, we can do software coding. Now we can see what is the advantage is that, let's say I need certain, like for basic sense, I need certain, you can say n number of protocols. Inside ARM processor, let's say I have only 2 UART, but in my design, I need 10 UARTs, 10 SPIs, and 10 I2C, 5 CAN bus. I need signal processing cores, many things I need. So ARM cannot provide all the things. Or what we need to do, I need to write a software code. So software code will be sequential, right? So it will be slower. But what we can do, I can create parallel hardware for each and everything. So you can see my design will be much faster, much efficient than working only on microcontrollers or microprocessors. And let's say if I want to develop a processing core inside an FPGA. So there also one option is there. We have soft core processors that is called microblaze processor. But it will not be as efficient as ARM because it will be spread out into LUTs, block RAMs, DSP cores. It will not be such as efficient as this ARM processor. So ARM processor will give that efficiency. Along with the FPGA fabric will give me parallel processing power. So we can have more like much better embedded system if we go with Zinc SoC designs. Right? And here the idea is, what are the things that we'll be using to develop the embedded systems? What are the tool ways? So we know about the hardware, that SoC that we'll be using, that will be ARM plus FPGA. But what tools I'll be using for the embedded development? So I'll be using Vivado to create the hardware mainly. I'll be using other tools also like system generator and HLS to create certain synthesizable cores. Along with that, I'll be using this VITIS IDE software development kit that is basically a Keil, a micro, or you can say Eclipse tool to write a C code onto the ARM processor. So this is how the Xilinx environment, you can say the Xilinx tools for hardware development works. Is it fine? Here we should know what tools is used for what purpose. That is the first thing that we should know. Is it fine? Can I move ahead? Any queries?
Yes, sir, clear.
Okay. So first 2 days we'll be working with theory only. Then from the third day onwards, we'll be having 5 to 6 days of session on Zinc SOC. So we'll be working on labs also. Yeah. So VTIS IDE is only used for software development. We cannot do any hardware changes once my hardware files has gone inside the VTIS IDE environment. So that is the main thing that we need to do. All hardware changes will be done in Vivado only. Any kind of software changes will be done in Vivado VTIS IDE software development. Yeah. So what will be the idea? How we'll be doing that? Let's have a flow chart kind of a look at. So we'll be using Vivado Design Suite. This is the primary hardware development tool. There will be can have two ways. I can use HDL designs where I can instantiate those primitives. That ARM primitive also is available, but the ARM primitives will have n number of inputs and output. So that will be quite difficult. But what we can do, let's say I want to create my own logic. Then I want to package it into an IP. So this hardware HDL design, I will package it into an IP. And we have this IP integrator tool that we'll be using rigorously. There already ARM processors that is in form of Zinc and all those IPs, ILAs that we have used, block RAMs that we have used, all those things are already included inside this IP integrator tool. So what I'll do, one by one, I will select it and I will create a schematic design, and then I will do synthesis, implementation, bitstream generated, and then I will send it to for software development. So this will be the basic idea of what will be used, how we'll be using Vivado Design Suite to create embedded hardware. Right? So now what are the possibilities? Since we have, now we can see the number of possibilities depends only on your imagination. Why? Because it is not restricted to the architecture of the ARM core. Now the ARM core architecture can be like improved or can be upgraded with any kind of an FPGA logic that we need. Let's say I want to create my own UART protocol that has different kind of baud rates, all those things that is not available in the market. I need to create my own logic that is not available in the market as a chip. So all those things I can do it in my in my FPGAs only. Let's say I have 2 ARM processors inside this one, inside my chip. I need to have 3 more processors. Then I can use this soft-core processor Microblaze inside the FPGA, and I can do intercommunication between this. Now my system has become a system of 5 processors, depending upon the space. That is the physical parameters will also always be there, but the possibilities becomes infinite. We have processing system that is fixed processors. I can have n number of software processors depending upon the requirement I can include. So this is Microblaze subsystem designs I can do. I can create n number of peripherals. Let's say I want to have CAN bus. I want to have, let's say, HDMI ports. I want to have, let's say, like something like audio, video kind of like peripherals I need to include. So I can include it in the fabric, FPGA fabric only, because it is a programmable hardware. So those hardware logic I can create, right? Accelerators or co-processors. Let's say I'm giving an example.
So Microblaze.
Yeah.
What is Microblaze?
Microblaze is also a processor, but it is a soft core processor. Soft core processor means it is not a dedicated hardware, right? ARM processor, as I told, it is already inside the chip. So it is a hard IP, hard core processor. But Microblaze is a soft core processor. That means the IP is available inside the Vivado. I can use this IP and I can implement that processor logic inside the FPGA itself. So as much as space is available in my FPGA, so n number of that many number of Microblaze soft core processors I can include. So let's say I have a system requirement where I have ARM processors that has already been used to work on some applications, right? But parallelly I want to work in another application, multi-processing system I want to create. So how can I create that? By using Microblaze as a soft core processor. You got the point, sir?
Yeah.
Yeah. So you can see here multiple Microblaze processors or
Sir.
other software processors we can include, and we can build a bigger system. Yes, please.
Sir, this microwave subsystem is like a IP.
Correct, IP.
So
It's
after
a-
instantiating it, we can it will use the components of the FPGA and it will behave like a processor, right?
Yes, correct.
Okay.
So let's say you need to have a processing kind of a logic. Processor kind of a logic means you will be writing certain instructions. That instructions will be processed, right? Sometimes opcodes, all those things, seek-based instruction I need to process. So if there is no Microblaze processor, what do we need to do? I need to write a full, we can say 8085 kind of an architecture inside, like with Verilog code. That will be very tedious, right? So already that's why such kind of requirement will be there. And this Microblaze processor is programmable. Why that means I want to have 32-bit version. I can have 32-bit version. I want to have 8-bit version. I can have 8-bit version. I want to have 16-bit version. I can have 16-bit version. I want to have let's say 1 MB of memory only. I can have 1 MB of memory. But this ARM architecture will be fixed. I can configure it. I can switch off and switch on certain variables, enable, disable, all those things I can do. But all the things that are present inside the ARM will be same only. Let's say I'm giving an example. I have 512 kilobits of L2 cache. It will not change. But here what I can do, since it is implemented on an FPGA, I can have 1 MB of cache memory here. I can have, let's say, 1 KB of cache memory also here that I can configure because this is a soft core processor. That is the advantage. So let's say, but what is the disadvantage? Let's say I want to have multiple processors, like multiple things coming. Like I want to have a very powerful processor, you can say. So if we don't use ARM, then it is a loss to us because Microblaze, if it is powerful, if we want to make it much powerful, if we want to make it bigger, then it will take most of the space inside the FPGA, and it will be slower compared to ARM processor. Why? Because ARM processor is hard IP, Microblaze is a soft core IP. So that is the thing. Everything there will be a trade-off. Depending upon the specification, we have to come up with an optimized solution. Is it clear? Is it fine, Abhinav?
Yes, sir, clear.
Okay. Yeah. So now we'll see what is the embedded system flow as a whole. We can see. So what happens, first of all, there is a system architect. It will decide which family that we need to use. What is the specification, performance specification? That is, those things will be done in pen and paper. As per the requirement, they will come up with their experience. They will come up with certain specification. Okay, this system can run if I use this family. I can, with their experience, they can say I can tune this system to 300 megahertz. I can have this much of power requirements, and this will be the behavior, right? So those things will be done by the system architect. Then they will divide the software development and hardware development. That will divide into 2 teams. Correct? So one team will start doing C code on just a rough version of the C code without any memory map addresses or anything. It will just write the main core, the main functionalities of the C code. It will start to work it out. And some of them, they will work on configuring the OS, what kind of OS is required, what is the specification of the OS, all those things. So that those 2 things doesn't occur one by one. Those 2 things occur parallelly at the same time. So what happens in this kind, basically from the electronic side, most of the people will work in the hardware development environment. So what they will do, they will start working with the design entry. Whatever the IPs that are required, they will create. They can use custom IP or Xilinx IPs or any third-party IPs, and all those IPs they will integrate and they will test it. So those things we know, in some ways we know, right? And then they will also validate it. We also know how to validate. Then they will put it as an XSA file. That is, all the hardware files they will export as an XSA file. XSA means Xilinx shell archive file. So what it does, basically, it will have all the hardware things that is required. So I guess you know about memory map IO and IO map IO. There are two ways to communicate with a peripheral or can communicate with a slave device. How to address it, because the processor, ARM processor should know, right? If there is a logic inside an FPGA, if there is a UART protocol inside an FPGA, the ARM processor should know its address, right? So that particular address, all those information will be given to the software development side. So on that, they will include all those things in their code, in that half build code. They will do testing, they will do validating, and finally that product will be done for deployment. So this is the embedded flow process that we can come up with. So what is the advantage of using that I'm focusing on, that is ARM plus FPGA, is now, depending upon the specification, since FPGAs are programmable, I can create any kind of a hardware that we need, and which will lead to creation of different embedded system with the same Zinc SoC chip only. But what is the thing is that we have to come up with our own hardware, we have to test it, we have to integrate it, then we have to send it to the XSA file where the OS configuration and some parts of the application development will be done at the software level. Only at the device level, which is which peripheral to call, what is the address of those peripheral, all those things will be combined, I can say, and then the full system will be validated and tested using both ILAs, you can see here, and here we will be debugging the software code, and then we'll be deploying it onto the system. So this is the way this embedded software, embedded system development works. So now if you see, it is a bit theoretical. So when I will demonstrate it, then we'll have a more like proper idea on that, right? So we'll have a rough idea on it. We'll have some practical demonstrations. We'll be doing parallelly. Yeah. Then we'll have more. Yeah. Tell me.
Sir, can you give an example where ARM is used with FPGA? Like when we are implementing, like we were writing HDL codes for half adder registers, like VRAM. There we are. There we were not using ARM, right?
Yes. As of now, we have not used anywhere in this session, in this internship. We have not used anywhere this one ARM processors, right? So I'll show you an example in my company itself where those ARM processors are used. Like, this is a good question. So yeah, so I guess you can see here, right? So yeah, so here you can see this analog to digital converters, all those things are front end RF part. From this part, you can see the waveform generation, signal processing, those things will be done inside an FPGA. Okay. So after that, those signals that been processed, it will be sent to the ARM processor, right? And finally, it will be provided to the outside world. So just to have more idea on that, to be more specific. So this is 1 second. Yeah. Okay. So let's say this system I'm creating. Abhinav, is it visible?
Yes, sir.
Yeah. So this part, what will be? It will be ARM processor, right? And these are external memory. So this peripherals, peripheral A, peripheral B, peripheral C, those things will be implemented on ARM processor. You got the point, right? So what is the advantage now? The processor, what it will do this one. It will do its processing kind of a thing. Processing in the sense, it will take those data. It will do decision making kind of a thing. Correct? And this peripheral, it will be there for a dedicated task. Let's say peripheral A is an ADC, analog to digital converter. So it is continuously taking the data, and it is and I am doing certain filtering work and certain signal processing work, and I'm directly transmitting it to the processor. Then on that data, the processor, it will be responsible to distribute it to some Ethernet, or distribute it to some external device, or to process it further, or to make certain decisions. But those things will be done in the processor. This FPGA fabric will be responsible to be created with this peripheral, and this processor will be controlling this peripheral A, peripheral B, peripheral C. So this peripherals will be there inside the FPGA. This processor will be there where a C code will be running, where the C code will be controlling the operations of peripheral A, peripheral B, and peripheral C. You got the point?
Yes, sir.
Yeah. So one second. If we have certain examples, that will be better. I'll give one. Yes, correct. So this is what I was. Yeah, you can see here. Yeah, so it's quite a good example. You can see. So this is like an you can say audio receiving kind of a device. Okay, so there's audio codec inside this one in like in the this one in the board, that, or this is an hard IP, not hard IP, it's a separate chip. So it is responsible to take the inputs from the audio inputs. Those data I am sending it to audio codec IPs, that is from Xilinx, and it will be implemented onto the FPGA. And I'm doing some filtering purpose. But this ARM processor, what it is doing in all those peripherals, it is controlling, it is taking the data, it is sending read and write information, all those things I am doing here. So the C code basically to control those peripherals, which will be developed inside the ARM. This is a peripheral IP, this is a peripheral IP, this is connected to this peripheral. That part, in this intercommunication part, will be done in the FPGA fabric.
Yes, sir.
Right?
Understood.
Yeah, fine. So these are the things that will be going to do, right? So now the main first thing that we'll be focusing on from tomorrow is, from the electronics perspective, we should know how to create hardware. But there is one particular problem associated with this, because all those things that we'll be creating, all those IPs that we'll be creating, will have its own generic address bus, data bus, or input, output, all those things, right? So there is no such any standardized protocols that while we are creating IP. Let's say when you are creating block RAM, input, output, all those things directly have connected, right? But to communicate with an ARM processor, we should follow certain protocols. So that is basically AXI based protocols that we need to follow, correct? So AXI is a standard through which the peripherals and the memory subsystem can communicate with the processor. And AXI is like a proprietary, like it's a state-of-the-art protocol for ARM processors, only for ARM processors. And since we are living actually inside an ARM processing environment, in your phones, if you see inside your Qualcomm chip, there is ARM processor. In your basic, like in your cars, in your washing machines, any kind of a smart device, there is some configuration of ARM processor. So that's why all the peripherals that when Xilinx has been migrating from ISC to Vivado, all those peripheral IPs that we'll be creating, if it is required that we need to connect to processor, all those should be all those peripherals should have, all the memory subsystem should have an AXI interface. So what I'm meaning to say is, all those information that will be passing throughout inside the chip should be of AXI interface, because the ARM processor can understand only when the data is been sent through an AXI standard. We'll discuss more about AXI standard, but this is the de facto standard through which we'll be sending data to and fro of ARM processor. That means if in any kind of a system, if there is a ARM processor, there should be an AXI interconnect. Or you can see the main thing is that it should be of AXI enabled, right? So using AXI only, we'll be communicating different peripherals, different memory subsystem with the ARM processor, right? Just to summarize about AXI, I will have this. So this is quite important. So what happens? We are into now ARM ecosystem. So ARM can accept data in a standard format. So that standard has been defined in AMBA bus. So the full form of AMBA bus is Advanced Microcontroller Bus Architecture. So it has different protocols. It has APB, Advanced Peripheral Bus. It has AHB, Advanced High Performance Bus, and it has AXI bus, AXI interconnect. So APB and AHB are not that much prevalent now. Most of the devices are working on AXI or ACP ports. So ACP, all those things are a bit higher, so we'll not go here. We'll be focusing in this point. So in Xilinx 7000 SoC, all the peripherals, or in Xilinx Vivado, that peripherals that we create should be of AXI specification. Inside AXI also, we have three types. We have AXI memory map, that is AXI full. All those things we will have a discussion. AXI light, we'll see what are the difference, and also AXI stream. So different requirement needs to have different protocols. But the main thing is to connect with AMBA bus, to communicate with AMBA bus. All those IPs that we'll be making from ourselves, or the hardware system that we'll be making, should be of any of these three protocols. So this is the second thing that we need to focus on, because let's say I'm making n number of peripherals, right? But the main objective is that at the end of the day, we need to communicate through AXI ports. So all those ports should be of AXI enabled. So when we'll be doing those labs, Xilinx already has provided all those AXI based IPs. So it is easier to connect with the ARM processor now. Is it fine? The concept of AXI, just I have given you an introduction. I will be discussing about AXI memory map, AXI light, and AXI stream. For working with Vivado to create a peripheral, I can say to create an embedded system with ARM processor using Vivado and Vitis tool, we should have an idea about AXI. Okay, fine. So this part will we'll take it off tomorrow, because we'll not have more information. We'll have a all those things that I have told, I'll demonstrate it first. That hardware design, software design, AXI protocols, I'll demonstrate it. Then we'll go. We'll again come back to the theory, and we'll have more discussions on this. Fine. Any queries till this point today? So better what we'll do, we'll work on the lab. I will give a demonstration on the lab. Side by side also we can work. Then whatever we have discussed today, it will be more understandable at that point when we'll be doing it once, right?
Sir,
Yeah, please, Abhinav.
can you send the recording after the class?
Yes. Now only I can send. Right.
Sir,
Okay.
yesterday
Yes.
recording actually is not got.
Okay.
Yesterday recording.
Yeah. Okay. Yesterday's recording also. Both the recordings I will send it now. Okay.
So from starting onwards, recording